Hi everyone, this is Brett Sanders, and this is the fifth instructional video using Primo. And in this video, we're going to tackle what's probably the most tedious part of setting up Primo, which is classifying grid edges to represent levees or gates. And the reason we do this is because the upscaling technique may filter out important control features, blockage features, or flow features that need to be retained in the model in order to accurately represent the movement of floodwater. And we've developed a method to adapt Primo to resolve that deficiency. And that method was published in Advances in Water Resources in 2022, and the lead author was Danielle Call. And it was called like Grid Edge Classification Method. And so I'm going to walk through that method now, like how we implement that as a pre-processing step in Primo and how we access it through input files. And my screen here you can see includes the basic input file, my terminal window, my MATLAB interactive window where I'm preparing files. I'm still using this Miami Gate test case, which I've used for all the other videos, and it's what's available inside the zip file, which you can download from GitHub or have access to in other ways. So to use the levee options and gate options, you can turn those options on here. So turn on the option here. And when you turn those options on, the code's going to be expecting to open a gate file to learn about gate information. And it's also going to be expecting to load a .levee file. So those files will be automatically written by a script that we prepared called Grid Edge Classification Miami Gate. So this can be opened, and it's a somewhat lengthy code here describing the method, providing some documentation of the steps. And I'm not going to use this video to sort of step through every detailed aspect of that process, but I do want to run it for you and just highlight a few things so that you'll know if you're doing things properly or if you've gone off course. You'll get a sense of what the method is supposed to do and how it's supposed to work. So right now this script is all set up such that if you run it, it will generate the input files that you need in order to use these features in the Primo gate test case. So I'll go ahead and just run that. But along the way it generates a number of files which are really instrumental for helping you to set up a script for a different site. If you're working somewhere else, you'll need to be able to set up these same types of files for other sites. So there's literally 5 different graphics that pop up here. And we're going to walk through kind of all these graphics so you can see what exactly is going on in the workflow. The first thing that's loaded is a digital elevation model and a shape file which shows the perimeter of the areas where there is levees or walls. And sometimes we add this grid edge classification to the banks of channels just to get a little bit sharper representation of flows. It might not even have a levee there, but sometimes having a polyline along the top of a channel bank can sharpen up the representation of that flow, and it's well worthwhile. Something here that's not immediately obvious is that there's also some gate structures inside this model domain. Right there is a polyline sort of representing the position of one of the gates that controls canal flows in this study area. And there is another gate down here. And so those are 2 places where we'd like to be able to classify edges of our model grid so that the model grid can then put in an appropriate flux function to represent the effects of that gate on the flow. So figure 1, 2, 3, 4, and 5 really show the workflow that's used to identify those edges that are going to be classified. The first step involves intersecting these polylines with the coarse grid. We're using an upscale factor of 10, so any pixel that's now yellow is a pixel that is being sort of a coarse grid cell that's being intersected by the levee. After that, we fill in all of the cells inside the levees. That's figure number 3. And then figure number 4 shows the outer edge of this surface, this yellow area. The outer edge becomes the location where we're going to enforce this sort of representation of levees. And if you can then zoom in to a particular channel reach, you can see the levee is naturally, this red straight line, but the high points along the levee that we want to make sure we enforce overtopping at the right threshold, those are all going to be represented at this jagged white line, which tracks the edges of coarse grid cells. So that's the idea there. So this whole process of intersecting the coarse grid with the polyline, filling it, and so on, that's all done in an automated way inside that script. And then there's some manual things that are done inside the script to clean up areas where the automation just isn't perfect. So, for example, the automation could lead to a levee edge right in here through the middle of the channel, and that's not what we want. We don't want a blockage effect there. We don't want a blockage effect there. We don't want a blockage effect there. So we want to make sure that we go back and remove the white lines. And you can see that maybe in this one as well. I'll zoom out. You can see that the processing chain leaves the ends of these channels open so that flow can go through them without a blockage effect. And that's also true, down here in this area. And you can see one little edge is sticking out there. It may not be ideal. Okay, so that's sort of the way the workflow proceeds, and you've got some parts that's automated, like intersecting polylines with grid cells and filling the area between, but then sometimes there's a few manual steps that need to go back and do, and you need to know like which edges, what are the numbers of the edges that need to be edited. And so figure 5 is really designed as a tool to help you see the numbering system of all the coarse grid cells. You'll see that there's numbers going vertically downwards here, 20, 40, 60, 80, and so on, and numbers going horizontally this way. And this numbering system corresponds to the conventions of numbering rows and columns in a raster grid, where sort of the very upper left-hand corner is the beginning of the data set, and you work your way downwards. And that's in contrast with a conventional Cartesian coordinate system, which starts in the lower left and increases in the x direction and increases in the y direction this way. So if we were to zoom in here, what you can see is that, as an example, whoops, that's not what I wanted. As an example up here, this location right here is intersecting row 12 with column 17. So that is centered in row 12, column 17. And the numbering of edges is always offset from the number of cells. So if this, for example, is cell number 12 right here in the row 12, then edge number 12 is right here, and this is edge number 13. Likewise, if this is showing to be column number 14, so edge number 14 is here, and edge number 15 is here. So keep in mind when you're numbering grid edges that the edges are always offset somewhat from the cell numbering, because there is in an n by n grid, there's there's an additional edge on the right-hand side and an additional edge on the top, and so on, that leads to a slight offset in the numbering. So let's do a little exercise here where we think about this white edge right here, and we ask ourselves, what is the actual edge number there? Well, first of all, we know that this is a horizontal edge, and those are different from vertical edges. So there's actually 3 grids that we're looking at here. We have a grid of cells, which are the rectangles. We have a grid of vertical edges, and we have a grid of horizontal edges. And the horizontal edges and the vertical edges can be numbered. This white one, since it's following after 10, that corresponds to the 11th row and the 17th column. So this is horizontal edge for row 11, column 17. This one here, as far as numbering goes, that is located, this is column 16, so this is going to be edge from column 16 and row 13. So that's a vertical edge, row 13, column 16. So that's how the numbering goes. And this figure 5 was meant to allow a modeler to sort of interactively look at the grid, look at where the edges are following, and in particular to go in here and find spots where, if we want to represent this gate, we're going to have to come up with a set of edges that intersect this canal from bank to bank, and we're not seeing any of those right now as far as I know. Let me zoom in here. I don't think are we seeing that here. We do see that edge has been tied in there. So it looks like in figure 4, zoom out again, that edge has been drawn in, and this one has been drawn in. Okay, so this script shows a completed set of grid edges that are used to represent this canal gate. A note here that in this particular test problem, the hydraulic infrastructure is more complicated than how we're setting up the model. There's a gate here, there's a pump over here, and the red lines represent sort of banks of channels. And instead of trying to deal with a complicated, one side is a pump and one side is a gate, we just called the whole one big thing a gate, and we're going to give it an ID. So how do we come up with that? Let's now zoom out just a little bit here so you can see. Okay, so we're able to see for this particular site, how the rows and columns are numbered. In this particular grid edge classification, there is a few spots where the modeler, the editor, needs to go in and need to manually specify some rows and columns to configure things. So one of those areas is here. This has to do with doing the grid edge classifications, and the rationale behind all that is discussed. And further down the script, there's another spot where the modeler needs to jump in and do some editing of the gate cells. And I must have just blasted past it. Here we go. So there's a note here on line 349 that you want to build this table interactively by viewing figure number 5. So in this test case, we had 2 different gates we wanted to build, one up here and one down there. So I called this gate number 1 and called this one gate number 2. And then you'll notice that there are both vertical edges, which are called gate V edge for gate vertical edge. And then there's also an array called gate H edge or gate horizontal edge. And then on this array, there is a table of information, which is the row, the column, and the ID for that edge. So it's expecting 3 numbers, a row, a column, and a number. So this is number 1 and number 1 here correspond to this gate, and all these 1s correspond to this gate, and these 2s down here correspond to this gate over here. So let's trace back to here all of the edges corresponding to gate number 1. So the first one is row 22. It's first of all, the first one is a vertical edge, and it's going to be row 22, column 31. Okay. So if we go to row vertical edges, row 22, column 31, that takes us right here. Okay, so that's one of the edges we're going to use. The next one is going to be row 21, column 32. So now we're going to be this vertical edge. And so we've got 2 vertical edges, and then we've got 3 horizontal edges, 2330. So 2330 is going to be, this is cell 23, so this is going to be edge 23. So this edge right here is horizontal edge from row 23 and column 30. And then we also have 2231. So 22 is going to be here, and 31. And then lastly, we have 2132. So 2132 is this one. So that means that we've connected a set of horizontal and vertical edges together to make up this path across, and that's what we see shown here in this graphic, this sort of zigzaggy pattern. So that's how we manually plot those. If, you know, say we make we sort of goof as we enter these and it doesn't work out. So say I accidentally put this in at 32 instead of 31. I can save that, rerun it, and then when you zoom in to figure 4, you'll see, oh goof, you know, something's not quite right in the way I set up the edges. That's not right. So then you check it out, it says, aha, this should be 31, and you rerun it, and then it'll show you that you've placed that in a spot that kind of creates the connectivity you're looking for in terms of a blockage feature. So all that being said, this script now has generated a couple of output files. It created a gate file, and it also created a levee file. And when you go into your input files, you can see that there is this gate file. And why don't we go ahead and open that up? What happens in the gate file is that this is automatically generated, but it's very intuitive information. You can always go back and edit it here if you wish. So the upscale factor is 10. There's 4 vertical edges, okay, and that goes back to this editing that we did. This file has 4 vertical edges and 3 horizontal edges, and the numbers match up here. So that's where we've got all of our information from MATLAB being written to a simple text file. Okay, in addition to that, we also have a file called gatecontrol, which gives us information about what the gates are doing. So it tells us that there's 2 gates. They're numbered 1 and 2. Again, we have a tabular data input file format here. There's an option to specify a discharge coefficient for the gate and also an opening of the gate, so how much it's open. Right now it looks like there's no opening at all, so these gates are supposed to be sealed off. Okay, so with this gate control then can either let you specify a constant opening for the gate, or we can open up a text file where information about the gate can be found, and that's a time-dependent gate opening. So if we go in here, you can see some input files with the G. You know, we open up those files, There's a header information. There's information here in the file, which is the length of the record, 8 points, the time interval of the data, and then the values of the gate opening for each of those instances in time. So that's the file format. You'll notice that the file format here is similar to just about all the time series file formats, with a header and number of length of the record, time interval of the record, and so on. Okay, so that is also set. Now there's no additional controls needed for the levee, but it is helpful to kind of just open the levee file and to see what it has done. What the levee file does is it reports the upscale factor that was used when this levee file was made, and it says how many different vertical edges are there that are classified, and what are the rows and columns of all those edges. And then it also reports the same thing for the, oops, skip past it, right there, for the horizontal edges, 555 horizontal edges, and there's a row, a column, and a levee location for each one of those. The levee location just says, is the levee to the left or the right of this edge? So it knows where to look for topographic data to specify the height of the levee. In PRIMo, you do not specify the height of the levee as an input file. It's just interpreted from the DEM itself. So what you're saying is that the heights of levees are already in the DEM, but they're at a fine resolution, and you might miss them in running your model on a coarser grid. So you're giving PRIMo additional guidance. Great. So with all that said and done, we've now got the options to use a levee turned on. We have the options for gate turned on. Let's add options for a point source turned on. And let's turn the rainfall off for now. So we'll put rainfall at 0. And let's just run this for an hour and see if we can get a simulation that we can interpret. So we've got the gates are active and they are closed in the sense that the opening is set to 0. So they shouldn't let any flow through them unless it backs up, water backs up and goes around it or over the top of it. So it is possible that the channel will just overtop and then water will flow around the gate, which is what you'd see, you know, in reality. So now we come back here and we go to our PRIMo-Viz Miami. Same input files or output files are generated. So we open this up, the water comes down these channels, hits these gates, seems to be building up, and just kind of blocked there. So there's an example of the gate sealing off those areas and not letting, you know, any fluid go further downstream. Now we can crank up the amount of water coming in and show an example with additional water. So let's do that. Right now we've got the point source turned on. I'm going to go ahead and take a peek at that point source file. Okay, so right now we're using input file, which is pulling flow rates, which are, if I recall, not especially high. So I'm going to just go ahead and turn off the time-dependent point sources and just use like these numbers of 20, which I know are pretty high flow rates that are going to overtop those canal gates. So let's just, with that modification, let's run it one more time. It should take just a little while. So in this case, we've gone from a time-dependent point source in 2 points in the channel to a constant point source of 20 cubic meters per second at each of those sources. There's a gate in each canal, which is closed, so no water can go under the gate, but if enough water backs up, it can go over the gate. So why don't we see if that happens. Water comes in, gate blocks the flow, it goes onto the land surface, spreads out, gets back into the channel and drains its way downstream. So this is a nice way to wrap up this session of using levee input files and gates in PRIMo.